All right, hey everyone, welcome back. So in the previous video, we introduced the concept of principal component analysis. We looked at some geometric examples. We reviewed the relevant background information, and then we figured out how to mathematically pose the problem of finding the principal components in PCA. And we ultimately got to the fact that the problem we're trying to solve to do PCA becomes the problem maximization of U subject to U having norm 1, U transpose X, U. So that was a lot of syllables, but that's the problem that we ended up deriving at the end of the video. And as a really brief recap, remember that PCA, what we're ultimately trying to do is find the direction in our data dimension that maximizes the variance of the data after we project onto that dimension. So we're trying to find the dimension U that maximizes variance, and the variance is this quantity, but the actual variance you divide by n minus 1. But like we said in the previous video, we could ignore that for the purposes of this optimization problem. So let's dive into how to actually solve this problem. And first, I'm going to go over a visual interpretation of the problem. Okay, so the visual interpretation is the following. So let me erase some of this scratch. Okay, so if you notice the optimization problem, we're optimizing over the set of vectors U such that norm of U is equal to 1. So let's visualize what this looks like in 2D space. So constraining the norm to be 1 is basically saying that the square root of U1 squared plus U2 squared is equal to 1, right? That's the definition. So if we square both sides of this equation, we get that U1 squared plus U2 squared is equal to 1, which is the equation of a unit circle in 2D space. So what we're saying, essentially, is that the set of vectors U is the set of vectors that lie on this unit circle. So for example, it could be this green vector here, which I call Y. So this is Y. It could be this red vector here, which is Z, or it could be this purple vector here, which I'll call A, okay? So those are 3 examples. There's an infinite number of these vectors, but those are 3 examples. And for each vector that lies on this unit circle, there's going to be an associated score that is given to that vector. And that score is going to be this formula, U transpose X, U. So for example, for the vector Y, there's going to be an associated score, Y transpose, X, Y. For Z, there's going to be this associated score. And for A, just to be clear, it will be A transpose, X, A. So for these 3 options, we're going to have the following kind of scores is the intuition I like to think about. And as always, we're always trying to maximize our score. So in this scenario, out of all of these different choices, we're trying to find the choice that maximizes our score, and our score is given by this function. All right, so you can think of it as kind of like a infinitely long multiple choice test where all of your different choices is each vector on this unit circle, and next to each vector is some number that represents that vector transpose X times that vector, and you're trying to choose the one that maximizes it. So hopefully that the problem is clear. And the way we're going to have to solve this problem is using the eigendecomposition and or the SVD. So these 2 are very related concepts, and we'll see them both kind of come into fruition as we derive this. I'm going to focus mostly on the eigendecomposition because I personally think it's easier, but we'll definitely tie it back into the SVD towards the end. So one of the important theorems that we use in this derivation is the spectral theorem, which, if you recall from lecture, states that for any real symmetric matrix A, there will exist a set of n orthonormal eigenvectors for that matrix. And n is the dimension of A. So A is n by n. Quick recap of definitions. So symmetric means that A is equal to A transpose. So if you flip the rows and columns, the matrix remains unchanged. And a set of orthonormal vectors is a set of vectors such that if you take any pair, so any 2 different vectors, then the dot product between the 2 is going to be 0. And each individual vector will have a norm of 1. So those are some definitions that we will use quite often. So the important matrix that we need to kind of analyze in our optimization problem, which I will rewrite down here, because this is what we're trying to solve, is this matrix right here. So X transpose X is what we're going to analyze first. And let's look at why that is. So remember that X is an n by d matrix, where the rows are the data points. So each data point is d dimensions, so there's going to be d columns. So if X is n by d, that means that X transpose X is d by d. So it's square, which is really nice. But what's even nicer is the fact that X transpose X is symmetric. And the way we can see this is by taking its transpose and using the transpose trick learned last time. This is the same as X transpose that X transpose transpose. So what I wrote here. And this part right here, X transpose transpose, well, that's just X because you're basically flipping the rows and columns and then flipping them back. So you get your original matrix, which is X. So these two match, which is exactly the definition of a symmetric matrix. Okay, the reason why we just showed that it is symmetric is because we can now apply the spectral theorem. So X transpose X is a real symmetric matrix. And so it will have a set of d orthonormal eigenvectors. D because that is the dimension of X transpose X. So let's call these eigenvectors. So let's write this down. D orthonormal eigenvectors. So I'm going to write E vectors for short. So let's denote these as V1 through Vd. And each of these eigenvectors will have an associated eigenvalue, lambda 1 through lambda d. An additional fact that is useful is a fact about these eigenvalues. And it's the fact that each eigenvalue is going to be positive. Or not positive, it's going to be non-negative. So each eigenvalue will be greater than or equal to 0. And to quickly see how this happens, let's look at the quantity Vi transpose X Vi. Okay, so this Vi is the eigenvector corresponding to lambda I. Okay, so this is the same as Vi transpose X. Sorry, this is the same as Vi transpose lambda I Vi, because remember that Vi is an eigenvector of X transpose X. So we use the definition of eigenvalue and eigenvector. Lambda I is a scalar, so we can pull this out. So we get lambda I Vi transpose Vi, which is the same as lambda I over lambda I times norm of Vi squared. This quantity right here is the same as X Vi non-squared. And to see this, first we can write this as we can first write that as X Vi transpose X Vi, which is the same as X Vi norm squared. So we've basically shown that this is equal to lambda I norm Vi squared, which means that lambda I is equal to X Vi norm squared over Vi norm squared. So if we divide, so the top, the numerator, is a non-negative number because you're squaring something. The bottom is a positive number, assuming that the vector is not the 0 vector, which it can be because it's an eigenvector. So the bottom is this. So if you divide two positive numbers, this is going to be a positive number. And it'll only be 0 if this numerator is 0. Okay, cool. So this is greater than or equal to 0. So let's use the fact that there are d orthonormal eigenvectors. Remember that if a set of vectors is orthonormal, they're also linearly independent. Okay, so that means that because X transpose X has a set of linearly independent eigenvectors, we can eigendecompose X transpose X, which we've used a bunch throughout the semester. So we're going to write this as V lambda V transpose, where V is, I'm going to write this as inverse first. So V lambda V inverse, where V is the matrix with columns of the eigenvectors, and big lambda is a diagonal matrix where the diagonals are each individual eigenvalue. Okay, now the key thing is that V is an orthonormal matrix. What do I mean by orthonormal matrix? An orthonormal matrix is just a matrix whose columns are a set of orthonormal vectors. Okay, a useful fact about orthonormal matrices is the fact that V inverse, if V is orthonormal, is equal to V transpose. And the way you can see this is by looking at V transpose V, which is equal to V1, V2, all the way up to VD times D1 ED. So if you actually do this out, then the diagonal entries of the resulting matrix are going to be the dot products between the same vectors. So the first diagonal will be V1 transpose V1. And because they're orthonormal vectors, this is going to be 1. But the off diagonals are going to be some vector, so like V1 transpose another vector. And because they're orthonormal, that has to be 0. So if you're confused by this, try writing out the individual components and then applying the definition of orthonormal, and you should get 1s along the diagonal and 0 everywhere else, which is exactly the identity. So V transpose V is the identity, which means that V and V transpose are inverses of each other. So V inverse is equal to V transpose. Okay, so why this is useful is because now we can write X transpose X equal to V lambda V transpose. So let's substitute that value for X transpose X into our formula. So then we're going to get maximization of U transpose. Now we can do our substitution, D lambda V transpose U. Okay, so it seems like kind of we complicated our problem even more because we have 5 different quantities here, whereas in the original problem we had 4. But what we're going to see is that each of these quantities has nice properties, most of which we've already talked about, but there's one more property that we need to discuss in order for us to really understand this. So let's talk about this last property, which is the fact that an orthonormal, move this aside, an orthonormal matrix V preserves norm. Okay, so what do I mean by preserves norm? Remember that we can think about a matrix V as a linear transformation on a vector. So if we look at V times some random vector X, well, V is going to do some sort of transformation to X, resulting in another vector. Now, if we look at the norm of this resulting vector, this is, if we look at the norm squared. So instead of looking at the norm, let's look at the norm squared. And let's simplify this. Remember that we can rewrite this as Vx transpose Vx equal to X transpose V transpose Vx. And because V is orthonormal, V transpose V is the identity. So we end up just getting X transpose X, which is X norm squared. So we've just showed that the norm of Vx squared is the same as norm of X squared, which is the same as saying Vx norm is equal to X norm. So even after we do the linear transformation that V does on X, the norm of the resulting vector is going to be the same. So there's no scaling that is happening. All that is happening is that V rotates or reflects X, but it does not scale. And a quick note is that V and V transpose are both orthonormal. And this is because V transpose V is the identity. Okay, so how are we going to use all of these facts? The fact that V preserves norm, the fact that the eigenvalues are positive, all these different facts. So the key lies in revisiting the geometric interpretation that we introduced at the beginning of the video. So let's look at this diagram again. So remember that we have this optimization problem that we've looked at many times. And we're looking at all of the different vectors u on this unit circle and trying to choose the one that maximizes this kind of score. Okay, so imagine a scenario where if we take each vector on this unit circle, so every single one, and for each of them, we multiply that vector by v transpose. So if we take a vector u on the unit circle, now we're looking at v transpose u. Okay, so for example, we can take this one, left multiplied by v transpose, and we'll get another vector. Now, we just analyzed that for an orthonormal matrix, such as v transpose, the resulting vector is going to be a rotation or a reflection, and not going to be scaled. So for example, if we take this green vector and apply v transpose to it, we're going to get a different vector. But this different vector is going to be also on the unit circle, because we're just going to rotate or reflect it by a certain amount, but we're not scaling. So a rotation on this is still going to leave us on the same unit circle. Same with this pink vector, same with this red one, same with this yellow one, same for every single vector on this unit circle. So what we're essentially doing, if we left multiply each of these vectors, is we're rotating this circle, right? We are taking the circle and rotating it. Well, rotating a circle doesn't change the circle. This set of points still remains the same, right? We've just rotated each of the points, but all of the choices, when you consider them as a whole, still is the same. So the intuition, the punchline is that the set of choices that we had before remains the same, even if we multiply each choice by v transpose. So the mathematical way of expressing what I just said in intuition is the original set we were considering, all the vectors u such that norm u equals 1, is the same as all the vectors v transpose u such that norm u is equal to 1, right? So even if we apply v, we just rotate all of these unit vectors, but we keep the overall set the same. But remember that this condition is the same as v transpose u equaling 1. This is the same as saying v transpose u such that norm of v transpose u is equal to 1. Okay, so, and we did this last step because the norms are equivalent. Okay, so continuing on, let's now define a useful quantity z. Let z equal v transpose u. So now we can take this mathematical optimization problem and rewrite it in terms of z. So this is going to be the same as the maximization of now z transpose lambda z, and the set of choices that we are optimizing over is now z such that norm z is equal to 1. And all we've done here is plugged z into this. So remember that we showed that these two sets are equivalent. So plugging z in gets us this. All right, so now let's see if we can solve this simpler looking problem, which we've shown is equivalent to this. All right, so let's actually write out what z transpose lambda z is for some z. So this is the same as z1 through zd, and a diagonal matrix lambda 1 through lambda d times a column vector z1 through zd. And if you do this matrix vector multiplication out, which hopefully shouldn't take too long, but for the sake of time, I'm just going to write it out. It's going to be lambda 1 times z1 squared plus lambda 2 times z2 squared, all the way up to lambda d times zd squared. So this is z transpose lambda z. And remember that we're trying to maximize this under the constraint that the norm of z is equal to 1. But this is the same as saying, so this is the same as saying norm of z squared is equal to 1, which means that if you take each component, square it, and add them up, you should sum to 1. So now we can rewrite our optimization one more time in terms of all of these internal components. So we can write maximization of z under maximization over z of lambda 1 c1 squared plus lambda 2 z2 squared. And we need to make sure that the sum of the zi squared is equal to 1. So let's look at this. Remember that these lambda values, each individual lambda value is fixed. It's fixed at a certain number. And what we have choice over, what we have control over are these z's. We can choose them to be anything we want as long as the sum of the squares is 1. We also know that each eigenvalue is greater than or equal to 0. So all of these are non-negative. So the way I like to think about this is that we have a bunch of eigenvalues. Each eigenvalue has, you can think of it as like having some sort of dollar value. So for example, you can have lambda 1 equal 1, lambda 2 equals 0, lambda 3 equal, say, 9. So this one is not that very valuable. This is like has no worth, and this is pretty valuable. It's the most valuable. And what we're doing with each z1 squared, z2 squared, zd squared is we're assigning a weight to each of these lambdas. We're saying, okay, let's weight lambda 1 by z1 squared. Let's weight lambda 2 by z2 squared. And let's weight lambda 3 by z3 squared. But we don't have unlimited weight. We only have a total of 1 weight. So we have a limited amount of kind of weight we can put on each of these values. And we want to maximize the overall like value we get at the end, right? We're maximizing this sum. So let's look at this example here. We have the choice of z1 squared. So we choose z1 squared, z2 squared, and z3 squared, right? Because that's what we have control over. We have control over z. So because we have control over z, we can choose these values. Okay, so if we want to maximize this sum, but also make sure that the overall sum of our weights is 1, how can we maximize it? Well, intuitively, we should give more weight to the more valuable items, where the items are our eigenvalues. So we should give more weight to lambda 3. We should give less weight to the kind of worthless ones. So in this case, the worthless ones are lambda 2 and lambda 1. In fact, if we have a limited amount of weight, why don't we just give all of the weight to the most valuable one, right? Because it seems kind of silly to portion off our weight and not give everything to the most valuable thing. If, say, we let z3 squared equal like 0.9, and that means that we have 0.1 left, so let's give like z1 squared 0.1 and z2 squared 0. So these sum to 1. Well, then our resulting value, our score, right, which is the sum, is going to be something like 0.9 times 9 plus 0.1 times 1. Okay, so that's what we get. But we want to choose the maximum we want to choose z that maximizes this. So can we do better? In fact, we can, right? Because we're kind of missing out by only assigning 0.9 to this most valuable thing. What if we just made z3? So what if we made z3 squared equals 1? Then our resulting score is going to be 1 times 9 equals 9. Whereas this is going to be 8.1 plus 0.1 is equal to 8.2. So we do better by just putting all of our weight onto the best one. And hopefully with this example, you see that you should always put all of your weight into your most valuable item, which kind of makes sense from intuition. So what does this mean? We have D. So let's look at the general case instead of this 3 example case. We have lambda 1, lambda 2, all the way up to lambda d. And we have associated weights that we want to assign. z1 squared, z2 squared, all the way up to zd squared. And let's suppose that, say, these guys are in order. So lambda 1, lambda 2 are in order from ascending to, so from greatest to least. So lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda d. So let's just assume this is the case. It's not a big assumption. We can always put them in order and kind of re-index them. Okay, so using the intuition that we just kind of developed, we know that we should give all of the weight to the most valuable eigenvalue. So we should give all of the weight to lambda 1 because it has the highest number. So this means that z1 squared equals 1. So assign these values. And because we make this 1, that means the rest have to be 0 because we have at most 1 weight. Like we can only give out a total of 1 weight. So that means that the rest have to be 0. So this means that the best we can do, right, the maximization, so the max of z lambda 1 squared z1 plus lambda 2 squared z2. So remember that we're trying to maximize this quantity. And through this previous analysis, we've just showed that this is equal to lambda max. So where lambda max is the max eigenvalue. Okay, and remember that this quantity right here is the same as what we were trying to optimize in the beginning. So this means that maximization of z, so remember z is equal to 1, z transpose lambda z is equal to lambda max. But again, remember from earlier in the video, we showed that this is the same as maximization of u subject to norm u equaling 1 of u transpose x u. So we've shown now that this value, the max value we can get, is equal to lambda max. So the maximum score, so remember going back to our analogy of having a bunch of choices and we're trying to choose the choice that maximizes our score. The best score that we could possibly get on this test is lambda max. Well, we know we've just found out what the max total is, but we've not really explicitly shown what choice gets us this max, right? Remember, we still have to choose this u to get this max. Well, it turns out that what if we just take u to be the eigenvector associated with this eigenvalue? Remember that this is just an eigenvalue of x transpose x. So let's look at the eigenvector associated with that. So let's look at v max. The eigenvector associated with lambda max. And let's plug that into our score function. Remember that each vector with norm 1 is going to have a score. And remember that x transpose x has orthonormal eigenvectors. So v max has norm 1. So let's plug that into it has an associated score. Let's find the score. The score is going to be v max transpose x v max, right? Well, this is an eigenvector of this matrix. So we can substitute this out and equivalently write v transpose lambda max v max. Well, this lambda max is a scalar. Pull it out. So it's going to be lambda max v max transpose v max. Now, remember that the eigenvectors are orthonormal, right? So this has norm 1, which means that v transpose v is equal to 1. So this equals lambda max. So the score for this v max vector is indeed lambda max, which is our maximum score. So again, if you think of this as some sort of test, and the most number of points you can get on the test is lambda max, well, you want to choose the answer that gives you the point total lambda max. And that answer ends up being v max, which is the eigenvector associated with the maximum eigenvalue of x transpose x. So the end result that we've just derived is that the best choice, so the best vector / direction, we say direction because we're looking at a unit vector, is the eigenvector associated with the eigenvalue or associated with the maximum eigenvalue of X transpose X. And the score, or the variance of it in that direction, which we just showed here, right? So we just showed that the score associated with it is going to be lambda max. So remember that the score is the same thing as the variance. So the variance along this direction, so if we project every point onto V max and take the variance, that variance is going to be lambda max. Okay, so now we're almost done with this video. I did say at the beginning that this has something to do with the SVD. And specifically, it has something to do with the SVD of X. So what is the relationship between what we just did and the singular value decomposition? So remember that in the SVD, if we take the SVD of X, what are we doing? We usually compute, step one is usually compute the eigenvalues and vectors. So we usually compute the eigenvalues and vectors of X transpose X, right? And that's going to give us a matrix V of eigenvectors and a lambda of eigenvalues. Except we just derived that the best vector is the eigenvector associated with the maximal eigenvalue. So if we do the whole SVD of X and we do the X transpose X way, remember that you can also do XX transpose, but let's look at the X transpose X way, then you're going to get X is equal to U sigma V transpose, where V transpose is V1, V2, all the way up to VD, right? Because there's D eigenvectors of X transpose X. And we usually write them in order of their eigenvalues. So lambda 1, the associated eigenvalues are in ascending order. And remember that each singular value is equal to the square root of the eigenvalue. So the upshot is that if we want to find the best direction or the first principal component of the data, so the best direction is called the first principal component, which is where the name PCA comes from, then all we have to do is find the SVD of our center data matrix X and just take the first row of V, or first column of V. Okay, so let me write that down and then we can summarize and conclude. So to find the first principal component, find the SVD of X and take the first row, or the first column, sorry, of V, where X is equal to U sigma V transpose. And the associated variance will be sigma 1 squared equals lambda 1. And the reason this is the case is because we typically order the singular values from greatest to least. So that's all the content for this video. Let's quickly summarize. Remember that the PCA objective is this optimization problem. And our set of choices in this kind of test is all the vectors along the unit circle. Remember, then we just looked at the spectral theorem and derived some useful properties that allowed us to basically do this change of variables. We saw that our initial kind of set of choices along this unit circle stays the same even if we multiply each choice by V transpose, right? Because we're just rotating the unit circle, but rotating a circle doesn't really change the circle. So that means that if we define this new vector, Z equals V transpose U, and substitute that into the original optimization, we can write it as a simpler optimization just using Z and lambda. And lambda is diagonal, which is super nice, because then we can write this as a sum of lambda 1 z1 squared. So we then kind of thought about, okay, our goal is to maximize this sum, and we have control over each z value, but we don't have any control over the lambda values. And the interpretation that I kind of thought about was, let's think of the lambdas as items with certain value, and the z's that we choose are how much of each item we buy, or how much weight we give to each item. So we want to maximize the total value at the end. So the intuition is that we should give more weight to the most valuable items or eigenvalues, and less weight to the less valuable ones, or the smaller ones. And in fact, we kind of showed through this intuition that we should just give all of the weight to the biggest eigenvalue and give 0 weight to the rest, because we have only a limited amount of weight to give out. So that means that if we order our eigenvalues from greatest to least, we should give all of the weight to the first one and 0 to the rest. So through this, we then showed that the maximum kind of score we can achieve in this kind of test or game that we're playing is lambda max. Now we have to figure out, okay, how do we actually achieve that score? What choice do we choose to get there? And we kind of guessed that it should be Vmax, right? Because this eigenvalue has to have an eigenvector associated with it. Let's just kind of try it out. And it turned out that, hey, it actually got us the desired maximal score. So that's the direction that maximizes variance. So that is the principal component, the first principal component. Okay, hopefully that video helped out, and have a nice day.